We've got a Q&A there. Right. Hi, welcome everyone. Thanks for joining. We're just letting people in through the lobby, so we'll just continue to do that maybe for the next couple of minutes to make sure everyone's in. Thanks for joining. Hi, Len, how are you? Okay. Okay, looks like we've got a good, healthy number to start. Welcome everyone. We'll just keep on admitting people as we go, but we've got great response today, so let's get underway because we've got a nice full program, but also plenty of time for Q&A as well. So welcome to this launch. My name's Donovan Story. I manage the CCAC, the Climate and Clean Air Coalition Technology and Economic Assessment Panel, the CCAC TEEP. Sorry, it's a bit of a mouthful. And I'll be providing some context about the work of CCAC TEEP, and then also introduce today and also the agenda and the key speakers. We've got a great range of key speakers covering everything from sort of the policy context right up to technical knowledge and experience through to really strong research experience as well. So my name's Donovan Story, and I'm joined by my colleague who you might see in the top right-hand corner there, working away, that Marco, who's joining me also from CCAC today. We'll be recording the session, so hopefully that's okay. We've got a number of people in different time zones, always a bit challenging to find the right time zone. This generally is around there, but we will also record so people can access the materials and the discussion afterwards as well. And because we're only able to really provide the launch live in English, it's very useful for people with English as a second or third language to be able to go back over the recording later on. So that's another reason why it's a great idea. So welcome. I still see a lot of people joining us. We've got a great crowd in today. So really looking forward to this latest launch of CCAC TEEP reports. We've had a number of reports that we'll talk about in a minute over the last couple of years. I think today we're focusing on a really critical issue in terms of what we refer to as a global landfill emission crisis. And that is the growing awareness of the role that waste, and particularly landfills and dump sites, are now playing in climate debates and discussions on mitigation actions and the need for those. And very clearly, as we can see through the COP process as well as one indicator, over the last decade or so, we've seen waste really move from being considered to be a local concern and a local problem for municipalities to now a global issue with global consequences. And along with those consequences, we need to find solutions, and we need to bring much greater knowledge and experience and interdisciplinary approaches to dealing with waste. Because again, as it's grown, as our understanding has grown in terms of the consequences of the global waste crisis, We need greater expertise and greater tools, but also options for actions. And one of the things that we're looking today is an option for action. And this is very much what the CCAC TEEP is designed to do, is to look at emerging, proven, but emerging technologies with the opportunity for scale and the opportunities for investment, in which we feel that the mitigation opportunities have not been explored to the extent that they could be, and also they lend themselves to actionable investments and technical solutions to be able to deal with mitigation, to be able to deal with, particularly in this case, methane greenhouse gas emissions. We know that landfills are playing this role. We see them visually now through IMO and other satellite data and technologies. We can visually see the importance of landfills globally, and we know that it's one of the most rapidly growing sources of anthropogenic methane emissions as well. The Global Methane Pledge, for which CCAC coordinates and acts as the secretariat for, has set the ambition to cut global methane emissions by 30% by the year 2030, and clearly waste and landfills have a key role to play in that ambition and set of goals. But we also know that often in the issues that we face in the climate and in the waste community as well, is that there's no magic bullet. That different contexts and different capacities and technical abilities, but also different development conditions lend themselves to the possibility of a broader range of solutions outside of one or two or three. So one of the things that, again, is important is to be able to look at different technologies, strategies, and regulatory frameworks which provide a smorgasbord, or at least a choice of actions which countries can take depending on their levels of capacity, their ability to invest, and also their technical knowledge and access to technology as well. So we need to look at a broader range of solutions than we have in the past. It's not just a simple matter of putting in a new landfill. It's not simply a matter of putting in one new piece of infrastructure or collecting waste in a different way, but we know it's a combination of actions, and this TEEP is looking at one of those actions as well. So the TEEP has been with us for a couple of years now. We are lucky to have great support from co-chairs, our co-chairs, one of whom has joined today, Peter Derry, from Ghana and Ireland. We also have an expert panel, and we're joined by one of those panelists today in the form of Amani. And we also have a high-level advocacy and advisory group as well. And really the goal of the CCAC TEEP is to be able to identify, to be able to undertake greater research and particularly practically oriented research and evaluation of technologies in different fields in the space of short-lived climate pollutants in particular, which are responsible for almost half of greenhouse gas-driven global warming in recent decades. So CCAC TEEP really supports what we'd call contextualized technologies, that is, technologies and approaches which are fit for purpose and that meet the needs and conditions by which we seek to implement them. And obviously looking at biocovers today is one of those solutions which we felt should be given much greater attention, should be a part of a much broader discussion in terms of a technology solution, a regulatory opportunity, but also an investment potential as well. And we're seeing greater attention now, particularly from multilateral development banks, on looking at solutions for landfills and to control emissions from sites as well. So far, for those of you that have been involved, or just you can look at our website to be able to see, last year we launched a major project on black soldier fly technologies. And in our agriculture sphere, we've launched reports on livestock digital extension services, and soon on digital extension services for the rice industry as well. and today biocovers and landfill methane mitigation. Biocovers, as many experts that are going to follow me soon, we see as having great potential. And the idea of this report, the whole philosophy behind such a report, and the materials which Marco has just put into the chat area as well for people to be able to access, is that they help provide decision makers, policy makers, entrepreneurs, investors, and project managers in understanding one particular strategy and solution that can be used at landfill. In particular, we're really excited about the biomitigation system in the area for landfill-based emissions, and today biocovers really brings attention to those opportunities as well. The report, and we're very lucky today to have the lead author Heo join us and also speak to us as well on the report. The report really covers a whole range of dimensions, which I think make it a really rich resource. It talks about suitability of context, the materials that can be used, the broader policy and environment and the strategy around general waste management and the role that biocovers can play. But it also goes into some really fantastic but very accessible technical and engineering knowledge on what makes an effective biocover system. But also, just as importantly, the context around which biocovers are not as effective as one might expect, and certainly the other solutions that can be tried, particularly in the discussion of passive and active methane control systems at landfill. And so biocovers are placed into a particular sort of solution category, acknowledging the fact that there are different kinds of landfills and dump sites which lend themselves to potentially other solutions which might be more effective. So biocovers have their place, and this report, I think, very importantly, sort of states exactly what that space and opportunity is, and also broadly looks at the costs of biocover systems vis-a-vis also their abatement potential. So there's the link to the report there. And today, again, fantastic range of speakers. I provided this introduction and we will be recording it. We have the Q&A area there for questions and comments, which we'll be constantly looking for over the launch. Peter Derry from the Ministry of Environment, Science, Technology and Innovation in Ghana, our co-chair, will be speaking in a moment. Amani will then speak. Heo will then outline the report and its technical inputs, and then Julia will come in for a broader sort of widening of the potential and opportunities, including linking us to some great research which has been conducted in the space, which people can follow up with as well. And then we'll have hopefully plenty of time for Q&A as well. We'll see how we go with that. So welcome everyone. Thank you for joining. Very excited about this launch. It's a great report. Visually, it's fantastic as well. Very accessible. Now available online. Really welcome you to engage with it, use it, share it across your networks, and to participate in today's launch as well. So thank you very much, and I'll now pass over to you, Peter.
Thank you very much, Denova, for those introductory remarks. And then let me say that I wish, on behalf of the co-chairs for the TIP, to welcome all of you to this very important launch of the report on the biocovers for landfills. I also want to use the opportunity to thank all who have contributed meaningfully to the report. I know it's taken quite a lot of hard work and a lot of commitment on the part of the contributors to make this happen. And as TIP, we are very, very excited, and we do appreciate you for those efforts. I want to start by saying that the launch of this report is coming very timely because at this point in time, the TIP is already discussing very important topics that should be considered by the panel. We are looking at technologies that are not only evidence-based, but technologies that are affordable and also adaptable, especially in the context of developing countries. And for us, I think that this report is a very vital tool to support that process. More importantly, if we look at the African assessment that was carried out by the CCAC and the recommendations that were made thereof, the landfills was identified as one key area that required interventions in order to reduce emissions, and particularly methane emissions. As it has been revealed in the report, about 11% of human-induced emissions are coming from methane, and this is even more or higher in the context of Africa. So for developing countries, I believe this report is going to be very helpful to guide policymakers make appropriate decisions, especially the fact that this is providing a technology or a solution that is much affordable, that is adaptable, and that has also been tried and tested in both developed and developing countries, as the report has revealed. And so, as co-chairs of the team, we are very elated to have this report launched today. And we want to say that the launch of the report is just the beginning of what it means when it comes to this particular technology. We as TIP will continue to take this up and try to advance this technology, make sure that this technology reflects at different policy dialogues or fora so that it could be considered for national level implementation. On that note, I want to say that we will continue to count on all of you as TIP as we go along for further research in different areas of topics and subjects that we are going to be looking at as a panel. And we hope that you would continue to support us as we go along so that we can achieve the very objective for which the TIP was set up. I therefore use the opportunity to congratulate the CCAC Secretariat and the TIP team for coordinating this process and making this happen at this particular time. On that note, thank you very much for the opportunity to say these few brief remarks. And I look forward to having a fruitful discussion with you all today, and as we move from the presentations to the Q&A session also. Thank you very much.
Thank you, Peter. Okay, Amani, the floor is yours now to set the scene of the context in which such solutions as biocover systems are being thought of. So I'm happy to pass over to you now to provide that broader context for us.
Thank you, Donovan. Can you see my screen in full mode?
Looks great.
Perfect. So yeah, thank you for your introduction and congratulations on the launch of this very timely report. Hello, everyone, and I'm pleased to be here today to present on the global challenge of uncontrolled waste disposal and climate impacts. So first, we're going to answer the question, why are we focusing on the waste sector? Then I'm going to provide an overview of waste management worldwide, the progress of dump sites worldwide, and then a particular focus on the methane emissions from these major dump sites based on our studies. So why the waste sector? The waste sector is often overlooked, yet it is the third largest source of global methane emissions, following the agriculture and the fossil fuel sectors. And methane emissions mainly originate from the decomposition of organic waste in landfills and dump sites. In the global south, over 50% of the municipal solid waste is organic, which end up in landfills or dump sites, with over than 90% in developing countries. And this is often coupled by open burning, that is releasing fine particulate matter, including black carbon and other toxic substances that are affecting the human health. Also, over 2 billion people are globally lack the access for basic waste collection services, which result in the widespread of the uncontrolled waste disposal, and under optimistic scenarios, only around 30 to 60% of waste is being collected in developing countries. Also, around 3 billion people, they lack access to controlled waste disposal facilities. However, up to 20% of the global anthropogenic greenhouse gas emissions can be mitigated through improved waste management and circular economy strategies. Yet these opportunities, they remain oftenly overlooked, and this is why we need to recognize the need to highlight more on the waste sector in terms of the global climate frameworks. So to provide an overview of the progress of municipal solid waste infrastructure delivery, we conducted this study that is covering more than 160 countries with dataset that include the waste disposal, the treatment, the recovery facility projects worldwide, and provide an indication of the total budget value of municipal solid waste development projects. For example, an indication in terms of investment in US dollars, the annual project capacity in metric tons, and the estimated power and or heat output in megawatts. And the results are disaggregated by country, by income level, by type of technology, as we will see shortly. And to the best of my knowledge, this is currently the only study that comprehensively tracked the municipal solid waste infrastructure worldwide, and it will provide country global coverage. So the results of this study show that the total investment is around 68 billion US dollars for this period between 2014 and 2019. And the total size of this implemented project is around 40 million tons per year, which is only 2% of the global annual waste generation, according to the amount of waste that is being generated from the latest World Bank report. And here, to provide an accurate indication of the progress of this infrastructure delivery worldwide, we're talking here about the projects that are only in the phase of implementation. Regarding the distribution of these projects in terms of income level, we can see that developing countries are home to lower fraction of these new waste management infrastructure projects. So this highlights there is a lack of investment in waste infrastructure in developing economies, and this will contribute to the continuous waste disposal in uncontrolled or controlled dump sites or landfills. Therefore, disposal to land remains the dominant disposal method in developing countries. And as a result, some statistic has showed that there are more than 1 million deaths per year that are related to poor solid waste management. 8.7 million people are at high risk from major dump sites in Indonesia and Philippines. There are 270,000 premature deaths due to open burning. And according to a report published by D-Waste that covers the 50 biggest dump sites, there are 64 million people that are potentially affected. And we're going to see also an update of these results based on our study. So based on the analysis regarding the additional waste management infrastructure that was delivered during this period and other data set from the World Bank report, we conducted this other study to assess the global status of municipal solid waste management and the amount of waste that is being generated worldwide. And this study showed that at the global level, only 58% of the waste that's being generated is managed through various alternative waste treatment technologies like sanitary landfills and others, whereas almost 42% of all the waste that's being generated goes to uncontrolled dump site or is openly burned. So this study is very important to inform policymakers and donors regarding the financing decisions and assigning budgets that need to consider the implications for cutting budgets or not providing budgets in certain areas. And this highlights the need of improved waste infrastructure delivery in countries of most need, like in low and low-income countries. However, these countries without sufficient financial capacity are mostly relying on donor funds to sustain the development of new infrastructure projects. So now that we know the amount of waste that is going to these dump sites, where are these dump sites located? To answer this question, we have recently developed this GeoWaste database and that are going to be presenting here that fill this gap. So our problem is that there is a very big lack of data in the waste sector, especially when it comes to uncontrolled waste disposal in the form of dump site, and we cannot manage what we cannot measure. So locating these different sites and understanding their characteristics and all the site level information can help us in improve the management of these sites and reduce the impact on the environment and human health. So here is a list of the main attributes that we are considering. First, we want the exact location of these different sites, their status, if it's operational or not, how long it's been operating, who's operating them, the amount of waste that's being received, their area, the type of waste disposal site, because in many countries, some of these sites can be reported as sanitary landfills, but in fact, they are mostly operating like uncontrolled landfills or dump sites. And we need also to cover the number of informal sector people who are potentially affected within a 10-kilometer radius, and the presence of open burning. And here is an example of Ghazipur that is located in Delhi in India, and it is the largest disposal site in Delhi, where there are more than 2,300 tons of waste that is sent to the dump site every day, producing a huge amount of methane. It affects more than 3 million people that are residing within 10-kilometer radius, with the nearest settlement only 200 meters away. It is polluting the local air, groundwater, and also posing serious threat to nearby lakes. And there are frequent fires at the dump site that are primarily caused by methane emissions during waste decomposition. And this is also exposing the nearby population to toxic fumes. And according to the East Delhi Municipal Corporation, the volume of waste at the dump site has reached a height of up to 65 meters that you can see here in the photos. This is like becoming Asia's largest garbage mountain today. And who works in these sites? It's mostly women, children, and vulnerable population. So what we have done in this database, we have identified more than 5,000 dump sites worldwide, and we're speaking here about large-scale sites and not the small ones. And then we have then sorted them for those where they had complete information and exact location. We then characterize them in terms of those that are active and also that are potentially causing the highest risks. So then in the next slides, I'm going to show you the results from these 200 major active dump sites. And this global database will help us to identify opportunities for mitigation and investment for emission reduction from the waste sector, which can create opportunities also for carbon market projects. And in 2014, the World Atlas report by DWaste, which identified the 50 biggest dump sites worldwide. After a decade, only 11 of these dump sites have closed, and the number of dump sites continue to grow worldwide. So the result from the study showed that here we can see the top 30 countries with active dump sites that are receiving 106 million tons of waste annually. The top 3 countries are India, Nigeria, and Indonesia, and we can see that they are mostly in developing countries. The total annual greenhouse gas emissions from these 200 major active dump sites is around 100 million tons of CO2 equivalent. There are more than 68,000 people working in the informal sector and 422 million people that is within the population that is within 10 kilometers of these sites. And this is equivalent to the population of Middle East and North Africa or North America. And these sites are by region, mostly located in Asia, followed by Africa. We can see here also the methane emissions from individual dump sites that are based on a model that we developed. This model builds on over a decade of work reviewing the waste sector emission methodologies, guidelines, tools that have been developed since the 1970s until now to account for emissions from the waste sector. And when I compare between these different models and tools, there is always a huge variability in estimated emissions. So even when you use the same input data, and mostly these kind of methods, they do not capture the emissions at the dump site. So hence this work to try to fill this gap and provide more accurate estimation in terms of methane and generally greenhouse gas emissions. So as a conclusion, the UN SDG 12.4 target could not be met by 2020, and there is an urgent policy intervention that are required. The closure of dump sites by 2030 requires an increase in the capacity of waste infrastructure that is being delivered in developing countries by fourfold. The full-scale deployment of a circular economy represents a radical change, especially considering the current functioning of our economic system. This requires innovative ways of rethinking the production system and consumption. Thank you all for your attention, and please feel free to connect and share your questions. Thank you.
Thank you, Mani, for providing that context. We'll hold all the questions and what have you. We're starting to gather them now till our last, once all of the presenters have presented. But thank you very much for providing that context, Mani. Obviously, a range of challenges, but also, I think, greater awareness of the role that mismanaged waste is playing in both our broader ecosystem, but also on human health and, of course, on climate as well. And in the context of looking at ways of controlling and managing landfills more effectively, you've looked at a range of possibilities and solutions, but as Peter raised earlier as well, these must be sort of fit for purpose. They must be well managed. They must be financeable. They must, if you like, provide the best options for countries and cities. And so that's the context in which TEEP is exploring different kinds of technology solutions, and which this report is such an important part of. And I think that we'll pass over to Heo now, and we'll really look at some of the key opportunities, but also the broader context for decision makers around biocovers and obviously methane mitigation oxidation systems in terms of their suitability, their abatement potential. Heo's report really gave a lot of attention also, I think, to design, which is very, very useful for those of us online today who want to know more about what does an effective biocover look like, but also examine some of the financing options and the finance and abatement potential of biocovers, which I think is very important for policymakers. And so there's some key policy messages there around what is achievable through biocovers and what more needs to be done as well. So to introduce the report and its key findings, very happy to welcome Heo Schaaf to the launch. And Heo, I'll pass over to you to highlight parts of the report which you'd like to give most attention to. Thank you.
Thank you, Donovan. Hello, everybody. Yes, I will highlight some of the findings of the report, but rather than going into a detailed description of all the chapters, I would like to try to raise your curiosity so that you will open it up yourself. The context has already been described by previous speakers, so there's only one thing that I would like to add, and that is at the bottom line. Landfill methane emission reduction is cheap. I personally do not know of any greenhouse gas mitigation measure that is cheaper than landfill methane emission reduction. And that means that the global population has an interest to maximize landfill methane emission reduction, because doing that with the least amount of money, they can achieve the highest impact. And as Donovan already mentioned, biocovers are one way. Actually, biocovers is a container thing that encompasses several methods, but we'll get into that. Thanks to CCAC TIAP, we now have a comprehensive report which is aiming at decision makers, and it allows in a step-by-step process, there are decision trees in the report to go through all the steps for a landfill that is somewhere on the planet, from a suitability assessment to a preliminary design, to a cost estimate, to a detailed design. And then finally, the last decision to make is to go to construction. It is focusing on decision makers, but it also contains a lot of comments that are suited for policymakers. And in addition, there is enough reference to detailed documents, other documents that have been provided by others for engineers. So based on this document, engineers can start actually making the design and doing the construction. Biocovers is an easy word. What we actually mean is microbial methane oxidation systems, but I will forgive you if you continue to use the word biocover, because microbial methane oxidation system is a rather long thing to mention all the time. They are particularly effective at landfill sites with the relatively low methane generation rates. That is because per square meter, the microbes have a limited capacity to convert methane into carbon dioxide. So these systems are particularly suited for landfills that have disposed low organic waste materials, that have disposed pre-treated waste materials, where basically most of the biodegradable carbon has already been biodegraded, closed or legacy landfills that are in the tail of the landfill gas generation, or poorly managed shallow landfills. The large dump sites, very high, we just heard Amani say something like 65 meters high, they may not be so suited, so they may require a different approach. Another major advantage is that microbial methane oxidation can be applied in situations without reliable power supply, which is not available in any situation all over the world. So the two things that are important to consider in design and construction is that besides methane, these microbes, and it's a huge group of microbes, also need oxygen. And if you want it to operate in a passive way, so not blow in with a blower atmospheric air, then oxygen can only enter from the atmosphere. And that means that the methane oxidation layer needs to be porous, otherwise the oxygen cannot get in. Maybe even more important is that the methane from the landfill normally exits the landfill through hotspots. So there is very local, high amounts of methane being released, and these amounts have to be distributed homogeneously over the methane oxidation layer to give the microbes a chance to oxidize the methane. So that means that porosity in the gas distribution layer is even more important than in the methane oxidation layer. To give you an impression, it has to be 10 to 100 times higher than the porosity in the methane oxidation layer. Now, there are many materials that are potentially suited to do this. Personally, I favor predominantly inorganic materials because they do not biodegrade by themselves, and that means that they also are not prone to settlement. So there is a lot less lower costs in maintenance, because even the most mature compost has a half-life of about 40 years, meaning that 10% of the volume is already gone after 5 to 10 years. And then the other important thing to observe is that if you put the materials, if you have selected the materials, you have analyzed them, and you have made the correct combination of materials with the correct porosity, and don't forget also to analyze for physical and other physical and also chemical properties. The microbes can deal with a lot, but there are specific chemical conditions that they do not like, and you want to give them a nice working environment, so be aware of that. If you have selected those porous materials, make sure that they are not compacted during construction. So the machinery that should be used should have tracks, not wheels. And as long as there is no vegetation and there is no developed root system, also be careful with people walking on the methane oxidation layer, because actually a shoe or a boot has a higher local compression impact than the tracks of a bulldozer. Sounds strange, but do the calculation. Now, then there is, of course, inspection and monitoring. Inspection is always necessary to identify vegetation damage, for instance, because vegetation damage is an indicator that locally a hotspot, high emission of methane is occurring. Settlement, cracks and erosion of the topsoil, and consequently then possibly also of the methane oxidation layer, should also be prevented, because these are also spots where uncontrolled emission can occur. Now, there are additional monitoring methods other than simple visual inspection, and there's a wide range and a wide variety, but I would like to say be careful not to over-ask, because as we will see later, monitoring can have a huge impact on the operational costs. So with maintenance and repair is unavoidable. Sometimes something happens. Maintenance is necessary anyways, because you have to do some mowing. Now here in the top right corner, you see a tracked mowing machine. That is not strictly necessary. Once you have a developed root system, you can also do it differently. You can even do it by hand if you have a lot of labor available and less access to machinery. But in general, repair of settlement and cracks, especially if you have to cover a bigger area, it requires the same precautionary measures to prevent compaction as during construction. Now, I've been working in the landfill industry for more than 30 years. And in these years, I have learned that there are only 3 things that are important in the landfill industry. The first thing is money, the second thing is money, and the third thing is money. So let's talk money, because that is important. If you do cost estimates, and there are some examples in the report, then usually a methane oxidation cover, the costs for a methane oxidation cover vary from 100,000 to 250,000 US dollars per hectare. Around 2/3 of these investment costs could consist of buying and applying suitable cover materials. So it is very important to look locally whether these costs can possibly be reduced. So you move from the 250,000 towards the 100,000 by locally available materials. And that can also mean that you have to go to organic materials. That may have a double impact. It could enhance composting, and it could also be that there are financing options through the composting. Repair and replacement is, however, most likely for organic covers, and they are the most important maintenance costs. Monitoring is also a very important annual cost, and the combination of annual maintenance and monitoring costs can vary between 3,000 to 24,000 US dollars per hectare per year. 3,000 if you do not do a lot of monitoring, 24,000 if for some reason an extensive monitoring scheme is required. If you then look into cost effectiveness, then you also have to consider what is the amount of methane emission reduction and then recalculate it to carbon dioxide equivalent emission reduction in, let's say, in this example, in 10 years. And for this example, I took a landfill, a virtual landfill, non-existing landfill that accepts 150,000 tons of municipal solid waste during 30 years. And after 30 years, the landfill is closed and a methane oxidation cover is applied. The average waste height is 25 meters and the landfill surface is 18 hectares. If you then construct a simple methane oxidation system, and in this case, inflation and net present value approaches have been completely ignored. This is just a depreciation of the construction costs in 10 years. So the investment in this 18 hectare landfill is 1.8 million US dollars, and it can go up to 4.6 million if you have a more complicated system with more layers than just a gas drainage layer and a methane oxidation layer. The operational costs can range from 700,000 euros, yes, sorry, US dollars over 10 years to around 2.5 million US dollars over 10 years. And that means that the total costs can vary enormously. Of course, the simpler methane oxidation system has a slightly lower methane and hence carbon dioxide equivalent emission reduction potential over 10 years, which results in a cost effectiveness over 10 years of approximately $6.50 per ton carbon dioxide equivalent. For comparison, the current carbon cost in the European trading scheme is 65 euros, which is something like between 70 and 75 US dollars per ton of carbon dioxide equivalent. So there's a lot of potential here. But if it has to be financed locally, then these $6 per ton of carbon dioxide equivalent, they could be in a feasible ballpark. Now, the cost effectiveness for the CDM, the Clean Development Mechanism compliant methane oxidation system, and the performance monitoring according to the Clean Development Mechanism methodology for methane oxidation layers is almost 3 times more expensive. And that is mainly because of the requirements in that methodology and the monitoring requirements. You then also have to consider that these costs are without verification of the credits. And verification of the credits can cost between $2 US and $20 US per credit, meaning that the costs can go 5 times higher than a simple methane oxidation system with no performance monitoring. And that's something that we have to consider because it essentially means that there is a need for other financing modes than the clean development system. I will get back to that, I think already in the next slide. Is that right? Why am I not moving down? Yes, now it works. Financing. There are various carbon markets that can potentially generate income for a methane oxidation project. But unfortunately, the income that comes from a voluntary market is relatively low. That will not compensate for the entire $6 per carbon dioxide equivalent in many cases. Now, the clean development mechanism methodology can no longer be applied because basically the Kyoto Protocol has ended. So there is now a transition to the Paris Agreement crediting mechanism, meaning that at the moment there are limited options for carbon market financing. Now, as I mentioned, the construction and monitoring requirements in the CDM methodology for methane oxidation layers makes the cost per ton of carbon dioxide equivalent relatively high. And I have searched the UNFCCC databases and I could not find a single project, 0 projects, that successfully applied with the clean development mechanism methodology for financing. So that already tells you something, that apparently this methodology is not working. Now, there are some proposals ongoing in the framework of the Paris Agreement to look at the methodology for assessing landfill methane emissions. And unfortunately, I have to say, I don't find these proposals very promising. I get the first impression that UNFCCC wants to discourage landfill methane emission projects. I have to look at them in more detail, but at first glance, I am not very optimistic. Having said that, there also are crediting mechanisms, methodologies for compost production. So it might still be possible also in the future that methane oxidation systems are eligible for funding through composting of organic waste. And then finally, and that is important for local decisions, that very often, we've seen a nice picture by Armani showing a landfill in the middle of a city. Closure of these landfills can increase land value, and it can increase the potential for alternative land use for municipal governments. So there is also some value to be achieved simply by closure. And that can then be done in combination with a methane oxidation system. So, in summary, biocovers are an interesting option for greenhouse gas mitigation in many situations, but assess your situation in advance. And thanks to CCAC TAP, a comprehensive report is now available that combines all the relevant aspects for decision-making and realization of biocovers. That report contains decision trees for an informed approach from a suitability assessment to construction of a biocover. And as I have tried to demonstrate, is that they can be very cost effective compared to many other greenhouse gas mitigation options that sometimes cost over $600 per ton carbon dioxide equivalent. So we should maximize the use of landfill methane emission reduction, as I mentioned earlier. It would, however, be very useful to develop new and simpler methodology for carbon trading. And I have a feeling that is possible. There are methodologies, for instance, in forestry that rely completely on modeling. And I do not see any reason why we cannot rely on modeling with respect to methane oxidation systems. We know what the impact factors are, and many of these impact factors, such as rainfall and temperature and porosity of the system, are easy to measure, and they do not change over a longer period. So there is also no reason to measure these over a longer period. So I think there is potential, but everybody has to be prepared to look into the options and not only continue on older methodology that, in my view, has proven to not work. So, with those words, I would like to thank you for your attention and give the floor back to Donovan.
Thank you, Heo. That's great. You froze for a little bit, but your voice went ahead perfectly, so that was okay. So that was the most important thing. Thanks for summarising that. There's been a few questions which have been asked, which we'll go back to after Julia has spoken to us as well. And I think they're quite useful questions actually. And I'd really encourage people to. Particularly Manolo asked a question about different sources of finance and what have you. Manolo, there's a lot more also in the report which Heo has developed in terms of potential options, and he started to mention those in terms of closure and perhaps carbon sink financing. And obviously the report also points in the direction of the GCF and other forms of green finance, climate finance, but also not easy to structure projects, as we know, to get the attention of global climate finance in this space. So I think that much more work needs to be done, and some people are putting up some nice sort of links and examples as well. But before we go to those questions, we have also invited Julia Jaber, who's joining us online, and Julia is most welcome to this presentation because as Heo was putting together the report, we had a lot of fantastic inputs. Of course, we had a great team, and I know that Kate's online and others really contributed a lot to the peer review group for this report. But Heo was very keen from the outset to involve a group called the CLEAR Group, which are the Consortium for Landfill Emissions Abatement Research, which Julia is a part of and represents. And it really points to a whole range of working groups that are in this space, that some people have sort of asked some questions which may be also answered by some of the resources that also Julia will share, as well as in the report, because there is a considerable body of research and analysis into methane mitigation oxidation systems, biosystems, as someone referred to as wanting to call them as well. And I think that Julia will point us in the direction of that work and also point to the relationship of research to practice as well. So the floor is yours, Julia.
Thanks a lot, Donovan. I'll share my presentation. So should be on. Good afternoon or good morning or good evening to wherever you all are. First of all, I would like to congratulate UNEP and CCAC-TIAP and of course the lead author Heo and all involved with this very, very impressive, good and above all useful document. And also on behalf of my co-author, co-speaker and colleague Marion Huberhumer, I would like to take a few minutes to give you a brief recap of the scientific efforts it took to enable this document, or that eventually led up to this document. I'm a professor of waste and resource engineering at TU Braunschweig in Germany and TU Delft in the Netherlands. And Marion is professor at the Boku University in Vienna. And together we chair the CLEAR group that Donovan already introduced, the Consortium for Landfill Emissions Abatement Research, which is a task group of the International Waste Working Group. And I'll show you a bit of the work, who we are, the kind of work that we do, and already now can say that you are cordially invited to join us or to request information from us whenever that is useful. First, briefly, who is IWWG? I'll trying to advance my slides, but it doesn't work yet now. This is just a screenshot of if you go to the URL iwwg.eu. The International Waste Working Group is a non-profit association, it says there in the top, and basically they have the goal to promote scientific advancement in the field broad field of waste management in the broadest sense. So we are a bunch of scientists that try to support sustainable developments, try to advance and disseminate knowledge in almost all aspects of waste management. And in that sense, we are a bit different from ISWA, the International Solid Waste Association, which also has a strong community of practitioners. As you can see on the left, IWWG entertains a number of task groups, of which CLEAR is one. A brief history of landfill oxidation research. It, of course, like many applied research areas, started with discoveries more in the realm of the natural sciences. So already 120 years ago, Zöngen, a Scandinavian scientist, discovered the so-called Bacillus mechanicus in wetland plants. Wetlands produce methane, so there are microorganisms that are associated with plants that grow in these wetlands, and the plants bring in oxygen through the root system, which then it can be used by these bacteria to oxidize the methane. So that's a long time ago, but then it took maybe some 80 years to discover their use and their presence in the landfill context, first published by Mancinelli and McKay, to my knowledge, methane oxidizing bacteria in sanitary landfills, a proceedings contribution, as you see here. Then, as we all became more aware of the risks of climate change as such, and the risks thereof, and the sources therefore, methane oxidation on landfills, received a boost in terms of a lot of funding for scientific research being routed to this topic. In 2002, CLEAR was founded actually in the United States on a conference in Asheville. And since then, a bunch of scientists into the field of emissions, not only abatement and mitigation technologies, but also simply monitoring and quantifying emissions, has stuck together with a core that has always been there, and then of course a project-based fluctuation around that core. And as you will see later, we've also produced quite some useful output, we think. In 2007, for the first time, methane oxidation, microbial methane oxidation, was listed as a key mitigation technology in the Working Group 3 report by IPCC. And overall, since about 30 years, we can say that using that research money that became available, countless laboratory and field studies on methane oxidation potential, the factors of influence, the ways to come to an optimized design have been carried out. Then we came from the lab to the benchtop to small scale studies, and since about 10 years, I would say, we have transitioned from research to implementation on full scale. So there are now a number of countries that have built and implemented and are monitoring these systems. And we are now, because that's the first generation of methane oxidation systems, we are in the process of then evaluating, it's an iterative process, and of course optimizing the design, because what seems useful from a laboratory perspective can be a very different reality if you scale up to the field. So that was a very brief history on landfill methane oxidation research. Who are the clear people? What do they do? We span all over the world. Currently from Australia to Canada, there are members from Europe, from South America, from Asia. We meet regularly in presence, usually in connection to the larger waste or landfill conferences. And there's always an afternoon where there is a clear meeting. In between, we organize online meetings. We hold workshops. We do site visits. Last year, or a bit more than a year ago, we were in Estonia, brought the whole group and interested people to Estonia to walk on a landfill, picture you see here, and discuss the methane oxidation system in place. We generate publications for everybody to use, and we also entertain a mailing list for informal discussion. So whenever someone has a specific question on a small, maybe protocol detail or whatever is of interest, we are simply a network of methane oxidation and emission measurement and abatement interested people that then help each other out, which is also a great opportunity for students and PhD students. On the, I trust you will receive the slides. On the lower left, you see our website and you see our email addresses as contact. If you have questions, would like to join the group, need information, please just contact us. Brief overview of what we have produced next to the, of course, very many conference proceedings, papers, and other sorts of publication that each of us scientists generates individually, but as a group. 2008, there has been a review led by Marian, where we first describe methane oxidation systems and published in Waste Management and Research. So what are they, general setups, how do they work? This was then extended a bit in another review led by Charlotte Schoitz from Denmark. There the process is a bit in more detail, and above all, it is a collection of data on systems that had been investigated at that point in time, giving basic data on the methane loading they had received, how efficient they were, and also introduces monitoring methods. In 2011, we were invited to host a special issue of Waste Management on landfill gas emission and mitigation. So there's a whole journal issue revolving around the topic. In the same year, we published the so-called methane oxidation tool, which is a simple Excel-based tool that is intended as a robust dimensioning aid to calculate with a few simple parameters what magnitude of methane oxidation rates you might expect. And once you know that, and you know the methane load that you want to treat, you can calculate how big your system should be. 2018, that was a news and views item and a workshop report also on waste management. Then lately, only 3-4 years ago, we published then finally a quite comprehensive review paper with very specific recommendation for the design of these systems. And the report by Hayo has used a lot of these insights and worked them into the report. Currently, we're working on practical small nuggets of practical guidance on very specific technical aspects. For example, if you want to measure the methane oxidation capacity of a specific soil that you would like to use, how do you then very practically do that, step by step? And these are expected to be published this year. So with that, I would like to thank you for your attention. You see here a 4,000 square meter happy, very well designed and very well functioning methane oxidation system on a landfill in northern Germany. having a very high efficiency and therefore low emissions. And I also find it a quite sympathetic and attractive vista. Thank you very much.
Thanks, Julia. It's actually the perfect image to end this series of presentations because it's such a positive image and it shows, as Heo was pointing out, and shifting from, the arresting slides that Amani showed of the reality of many global landfills and dump sites that, such things can be achieved and it is possible, particularly, I know we have colleagues online that have been a part of the recent Latin American ministerial commitment to close and cap landfills in Latin America over the next 10 or 15 years. And they are looking at such systems like this in terms of basically the closure, obviously the moving away of organics and other forms of waste away from landfills, and then systems which can manage closure, knowing that landfills continue to emit methane, for example, for several decades after closure. And yet many of them, particularly the older landfills and dump sites, are in very important ecological areas and sometimes sensitive ecological areas because that's where land was cheapest, and sometimes very proximate sort of sources of land to large cities which have grown beyond them. So they act as a vital green space in many cities. And I know that, for example, that Seoul in the Republic of Korea has transformed a lot of landfills that were very, very poor state in the late 1980s into basically parks, urban parks, and community areas, and have closed and capped those landfills and turned them into really vital green spaces. So these things are possible, and such images like that remind us of what we're all hoping to get to. But thanks also from a personal perspective of walking us through, some of the scientific understanding and basis of methane oxidation bacteria, right the way through to wetlands to its application, right to modern day landfills, and taking us through that story, because it's a really important one, because I think increasingly we're looking at solutions, aren't we, globally, which are more nature-based solutions, which are smarter solutions with our ecology. And I think this really pointed to the fact that biosystems, I'm going to call them biosystems now because Alexandra's convinced me to use that term for the next 5 minutes, can really play a positive role in terms of our ecology, as well as dealing with some of the pollution issues, which obviously are created through unmanaged landfills. I've got about 3 questions I'm going to throw out. One of them is a reasonably obvious one for Heo, and I know it's dealt with a little bit in the report. So Alexandra is also posed, I don't know if you can see the Q&A area there, Heo, but it really talks about problems of water blockages, cracking, and management of biocovers, which have proved disappointing in some context in terms of that hotspots are created through that crackaging and blockages. And he's wondering how that phenomenon or problem has been addressed in the report. And I know you gave a lot of attention to porosity and management. So if you could just maybe draw some attention to problems that have been experienced elsewhere in terms of water pooling, of cracking, and of blockages. Thanks, Heo.
Yes, unfortunately, the most of the full-scale projects that are known, they have been applied in moderate climates. And moderate climates do not suffer from heavy rainfall over a couple of hours usually. That's going to change, we all know that, but the experience is not yet there. It is, however, possible, but then you have to get a civil engineer in, because civil engineers, they are familiar with designing drainage capacity of porous materials. So if you are in an area with heavy rainfall, yes, you can still design a biocover, but you should give special attention during that heavy rainfall period to getting rid of the water by means of drainage systems. And of course, the contradiction that cannot be avoided is that the methane has to transport upwards and the water is transporting downwards. So they are in competition with each other. That is not easy, but it can be done.
A further question came, Heo, that I'm not sure if the report sort of directly addressed it. In part, it addressed the opportunities around passive and active systems of gas control and of methane abatement. But one of the questions has come up that in terms of a semi-aerobic landfill system like the well-known Fukuoka method, can biocovers be used in combination with such strategies and systems?
Theoretically, yes, but of course, the Fukuoka system uses what I would like to call chimneys. And these chimneys are very local. Let's say they are humongous hotspots. They are incredibly big hotspots, basically. That is what they are. So you would have to somehow distribute that homogeneously over a methane oxidation layer, and that could be a bit of a challenge. Because usually, if you have a methane oxidation layer of about 1 meter thick, it is already a challenge to get the methane from the bottom distributed over 10 meters horizontally before it gets up 1 meter vertically. Now, if you have such a concentrated high amount of landfill gas, you would probably have to use mechanical methods rather than only passive methods to distribute that gas homogeneously in order for the microbes to effectively oxidize that.
Right. That question came from Letitia. Thanks, Letitia, for that question. Really good one, because obviously a number of countries have gone down different system pathways in terms of managing landfills, and it's really important to look at the relationship of the effectiveness of biocover systems or methane mitigation systems with other systems that are currently sort of in play. Khalil also asked a question. It was cut off, unfortunately, Khalil. I can only see the top of it. Just asking, I think we did talk about the CDM methodology quite a little bit in terms of its limitations and why it's not used anymore, and maybe looking forward to active or future methodologies which may be more supportive of biocover systems. Do you want to reflect on that one more time, just for Khalil?
Yeah, there are 3 main problems with the no longer valid CDM methodology. One problem is that it is capped at 60,000 tons of carbon dioxide equivalent. So even if you generate more credits in your project, it is capped. You are not allowed to exceed that level, which means that you actually can only get financing for relatively small projects. Not the bigger landfills, relatively small projects. Sometimes that is not a problem, but sometimes it is. Now, then there are very high requirements. I think they may come from Germany or Austria. That is how I interpret the technical requirements on the methane oxidation layer and the gas distribution layer and the humic topsoil, etc. So it does not leave you all the flexibility you may want to have in order to reduce costs by applying a different approach or a local material. And the third and maybe the most important reason is that there is a very intensive monitoring program that, as I have tried to explain, can triple the operational costs of a methane oxidation system. So that is All three of them, but probably the monitoring is the most important reason why this particular CDM methodology has not been very successful, in my view. But okay.
I think that's terrific, and I think again, I really encourage people to look at the reports. A couple of chapters there on financing, which go into quite a bit of detail. Has provided a nice sort of evaluation of CDM and its limitations, but also looked at other forms of financing going forward as well. I don't know if Julia, you can see that question, but somebody, Dennis, had a really good question from your last slide there, particularly from the Sardinia symposium, of the use of landfills and then growing energy crops on top of them. And the report itself, there's actually an image of one biocover system which is now completely covered with solar panels, which is from East Asia, and again the reuse of land in terms of energy creation, but also alternative uses. So, Julia, can you unpick the mystery of that photo, whether we're reading too much into it?
I can. Thanks, Donovan, and I also see the question. No, these are not energy crops. This is the result of, you saw these nice flowers. It's a natural seed mix of grassy vegetation that has some herbaceous flowery vegetation in it. And that is a good question to ask, because it stresses the fact that we not only need careful layering and material selection, it's all explained in the report, but also that the vegetation that we choose is very important, because the vegetation actually has several functions. It keeps the soil or the biocover material from eroding, so it keeps it in place. But if you choose a vegetation that has a dense, more or less spatially homogeneous root network, it also greatly supports to homogenize the gas flow, both from below, which would be landfill gas, as the oxygen diffusion from the top. What you must not do is allow for vegetation, and maybe that is then part of basic maintenance, for example, thistles or other vegetation that has one strong root that grows downward quickly, because in that way preferential pathways and therefore the risk of hotspots are created. So this was a mixture of material that would have a more homogeneous root network. Also, the goal here was, this is a landfill. We discussed the value of green areas and urban spaces, and I agree that landfills play a very important role here. And this landfill particularly was developed by a landscape architect to fit in with the surrounding landscape and be a landscape park. And the gas treatment system, in this case, they were methane oxidation filters, although very big. I mentioned the thousands of square meters. One requirement was that they should visually fit in with the green vegetated surface of the landfill cover. So this was how the choice was made.
Thanks, Julia. We've only got time, I think, for one more question, and I want to make sure that Amani gets a tough question to answer as well, to take the heat off other people, and also to go back to that great presentation. Amani, I don't know if you can see the question from Dennis, but Dennis was asking whether in your research you covered possible resistance from informal sector groups working in these systems in the Global South, and with respects particularly to livelihoods from the informal sector and systems such as biocovers or dealing with landfills in a more controlled fashion. Do you see resistance to such systems? And I think it's a really great question to finish on, actually, because it's something that we talked about really early on when HAO was starting, was the whole issue around livelihoods and displacement in terms of managing landfills. And I know that obviously Nobody wants to ever see people having to make their livelihoods from landfills and in very dangerous conditions. But the reality is that millions of people do. And in addressing landfills in different ways, we have to accommodate their livelihoods and their needs. Sometimes on landfills, on or around landfills, for example, on social cooperatives or recycling systems, and off the actual landfill itself, but creating jobs around landfills. And in some cases, it's more difficult to find that accommodation. So could you reflect on, what you've heard today in terms of this deep work going into looking at a solution for obviously a greenhouse gas problem and an environmental and a health issue as well, but also in really reflecting upon solutions such as this or strategies such as this, how do we accommodate those making livelihoods from waste?
It's a very hard to answer question. Of course, the talk today is more on the focus on waste and the climate agenda, but the impact goes beyond that, and we need to focus on especially the social dimension, which is very important, and the public health. In the study here, we don't really like it's based on what have been reported. So basically, it's not only limited to identify the locations of these sites, but we need to understand not just looking at an image, okay, and then we have this site that is located here, or the number of sites, but to understand more about the social dimension. So we need to know these sites, how have been they operating, who's operating them, the number of informal sectors. So here we're relying a lot on some kind of whatever figures have been reported in some countries, but in most of the case, we don't have these figures. So we kind of done some kind of modeling to understand and kind of estimate the number of people that is present in these sites that are either working or living or kind of informally kind of working. So we don't really have we're not really working on the social dimension in very kind of deeply, comprehensively to understand all the specific things, but it's important to highlight on this issue and bring it to attention the people who are informally working or residing in these sites, but also on the nearby population that can be potentially affected, to kind of provide a safe transition. And here the focus was specifically on the results I've presented here on the uncontrolled waste disposal sites, and specifically dump sites. So we've done also a lot of work to kind of recharacterize these sites. Kind of in many cases, they are in some countries reported as sanitary landfills. Some of the nice pictures that Julia have been showing, and also you, but in the developing countries, most of these sites are not really sanitary landfills, and they are operating more like a dump site. So we were able to characterize them based on international guidelines. And this is something really important. And at the end, using this climate agenda, right, if we finance these kind of sites and we reach the closure of these sites towards these technologies are being presented in the report is being launched today, we can provide a safe transition and also save on the greenhouse gas emissions. So, yeah, thank you.
Thank you, Mani. It's a really nice conclusion for today, actually, and to remind us of the broader dimensions. And I don't know if probably some people were able to join yesterday, but actually CCAC hosted a webinar yesterday called Women Waste Workers as Climate Actors, and used experiences from Brazil and South Africa to show how climate solutions can actually be found by working constructively with the informal sector. And if people go to our website, they should be able to see a link to that. And I hope it was recorded, but at least there'll be the information and hopefully the presentations of that. So that was called Women Waste Workers as Climate Actors, and we just hosted that yesterday. So thank you. I would just like to thank everyone for joining today. There's a lot of webinars all the time. We had almost 140 people join us today, which is fantastic. I'm really proud of this report. Thank you, Heyo, and thank you all those that contributed to it. The TEEP team, Peter, for joining us today as a co-chair of the CCAC TEEP. We've got a number of reports coming out this year, which really look at the intersection of technology and finance and solutions which lend themselves to scale and impact. I wanted to thank colleagues like Marco, who were so important through this process as well, and also a couple of silent but incredibly important contributors to the report, Kate Siegel in particular from Clean Air Task Force, who provided a lot of comments on an early draft and really helped us, as well as members of the CCAC Waste Hub, Anya Svetcha as well, really led a lot of really positive reports on early drafts. Please use the report, please share it, disseminate it, keep communicating on it. It's there as a public resource, and we hope it helps contribute to ideas. We hope it provides a good evidence base for those supporting methane oxidation systems and biocovers, and we really hope that it finds a good home out there, and we'd like to keep in touch with everyone through future reports, and also the TEEP. Also happy to hear from people as well, and you'll see the links to our website. Thanks everyone, thanks to the speakers, have a great day. Thank you, Peter.